have the InfoSec talk about cloud security by Thomas Fricke, who's known for his work in cloud security specifically and also member of the Innovation Network for Public Health in Germany, a network that's focusing on public in the sense of for the public good and not for, well, other sometimes abuse of this name. So give it up to Thomas Fricke for Can We Trust Zero and Zero Trust?
Thank you and the entire Angel team for the wonderful organization here. So let's go into Zero Trust. That's me, what I've done so far. Started centuries ago, feels like that. Statistical and quantum physics, long time Linux, doing mostly system automation now, DevOps, cloud security. And what I've learned on this camp, that these 3 projects, I've done more, but these are the successful ones. So if you follow digital sovereignty from the German perspective, and if you speak a little bit of German, you can look into it and you can reuse it. Feel free to do anything what you want to do it. I'm doing Kubernetes now for 10 years, and so the examples will be a little bit Kubernetes specific, but can be generalized. So what's a zero? Effectively, everybody thinks this is this O-like symbol, but originally in the Arabic ciphers it only was a dot. So the zero was really limited to very small amount of area and did not contain much. And this Western version of zero is more or less the bloated version of a zero. And so we will see what's going on in the bloated version of a zero with trust. So what's trust? We have to define it. If I trust somebody, I don't have to check what he or she is doing. That's the definition of trust. I don't know if this is real. And the opposite is no trust, zero trust. This means I have to check more or less always what you are doing. So this is a complete mistrust, and I have to find out the balance, what is needed in my environment. And we had actually kind of security model which is based on the medieval castle. So this is a map of Belvoir Castle. This was the original castle, influenced the design for several centuries. You have typically one moat, 2 walls, towers, bridges, and it took 18 months until it had to surrender. So it's quite stable, and this is our security model. But if you feel well with this castle, this is our current situation. So there is no possibility to build a moat or a wall if you are in a sea battle, and this means everything is moving, and this is effectively what happens in the cloud and in Kubernetes today. So everything is moving, and this model with walls and moats is not working anymore. And especially this castle model has a problem. We have to pass the zone from the interior to the outside, vice versa. We have seen this wonderful talk yesterday about hypervisors, and everything which goes wrong is at the border of one security zone. So if you pass the security zone and the guard is drunken or has a is not trustworthy, then you have a problem. So you have one moat, and you're on over a moat you need a bridge. In a wall you need a door. Towers have guards. You need bridges with drawbridge mechanics, and if you want to stay alive 18 months, you need enough stock in your castle that you survive this amount of time. So that's the thing. And here you see the real castles on the left side. So you see our network castle, which is with several security zones. So you have in the middle you have the zone A, restricted high security zone. Zone B is high security, and then step by step you lower the security till you are outside. And in CPUs, you have a similar construct. You have a ring 0 up to ring 3. The ring 0 is a privileged one. And then 1 and 2 are for device drivers, and user space applications are normally in ring 3. And if you have to pass one task or memory from one ring to another one, then you have to be very careful that you don't expose risks this way. So this is the CPU castle, more or less. Another example is a microkernel. So you can have trusted microkernels. For example, something like the Nova microhypervisor, 9,000 lines of code, and it can be proven. The proof took 2 years with the help of a proof system, and then you are sure that you can absolutely trust your microhypervisor. And then you have additional code for pathing things, and you cannot trust your Linux system because Linux has so many drivers and such a bloated code base. You have to isolate it. It's better than the other system we all know, but effectively nobody will guarantee you that that 20 million lines of code are completely free of security errors. This is the basic problem. If the guard at the border is corrupt, like a hidden backdoor in firewalls, nearly all firewall products have a hidden backdoor more or less on a monthly base, then you cannot trust your firewalls. You have hypervisor breakouts. We have seen this yesterday on the main stage. We have kernel drivers who are outdated or corrupt. And we have even processes which have to be trusted. So there is an attestation process. I will go deeper into it if I talk about the secure enclaves. And behind the scenes, you have to trust the embargo process of reporting security bugs. We had this problem with Microsoft SharePoint, and it looks like, it smells like in the moment that the embargo process was broken, and some hackers of a country had access to this problem before the problem was fixed. And overall, in clouds, you also have under your hood firmware update processes. So firmware updates normally take 6 months in a cloud environment. This is a long time where you have to trust that nothing happens. And yeah, so the perimeter model is a little bit outdated, even if we have to implement it sometimes. And then people started with zero trust. And in the beginning, it was only zero trust network access. So we don't trust our own network, which means we have to check every connection on both sides. You have server-side and client-side certificates. You have authentication everywhere. You have a certificate authority, and you behave as you already have intruders in your network. And this is strange. So you have to limit the damage intruders can do. This is obvious if your company has a bring your own device policy, then you have to isolate it, and probably some of these devices are hacked somehow. So you behave as you have an internal attacker, and probably if your company is big enough, you have an internal attacker somewhere. And if you are important enough, you can be sure that you have more than one internal attacker. Solutions, we had SSH, mutual TLS, VPNs. This is a network side, but SSH is broken because the key management is broken. The original author of OpenSSH reported in a meeting some 10 years ago that after he has left his former company, 150,000 systems had his original key on the server side. So it was never revoked. You can limit, and you can even sign SSH keys, but nobody does it. Or is anybody here signing SSH keys? Great, you are great. So you have the typical life cycle of something, life cycle of keys. You have host keys. Most host keys are ignored. You have this CA chain. You have point-to-point communication. And you have always a problem of the initial key exchange. So how do we do it in the beginning? So managing SSH keys with Puppet or Chef or Ansible is not a key management solution. Same is for VPNs. So if there's so much implicit trust, then yeah, and we don't want to trust anybody, then we have a problem. So effectively we are in paranoid mode now, and there is a catch-22 citation. Just because you are paranoid, this does not mean that they aren't after you. So we have to be prepared. One example, so this is an old version of Istio and it has been fixed somehow, and I made a hack, by the way, and unfortunately I was only the second one to report it. The Istio hack means we have inside Kubernetes a special mutual TLS network, which means we spawn proxies everywhere. This is effectively what is called a service mesh. Every payload gets a sidecar container, and the sidecar container has full control about the traffic. So you cannot bypass the sidecar container unless you notice the sidecar container is running with netadmin privileges, and so in that version they have fixed it, fortunately. In that version the entire pod run with network admin privileges, which means you could even, with a little knowledge of IP tables, you could revert it, and that means you implicitly trust that your pod is sane and it does not exploit the netadmin capabilities. And attached in this picture you find a certification authority, so it's called Citadel in Istio, and it can be attached to a hardware security module, but nobody does it. Talked about the privilege container, you are in the same network. Yeah, and they have fixed it somehow, so you still can have sidecars, but now you need to know what you are doing, and they are aware of it, and then finally you can get also containers, Istio containers for the entire host. So this would be, if you don't know Istio the model, you have here two pods and they get injected this Istio envoy container additionally, and it takes over the communication, and in an init container the network admin was set up, and everything was privileged, so you could revert it by sending a privileged container. This is known. And now the next level is, if you hear in all the clouds at the moment the discussion about digital sovereignty, earlier or later, mostly earlier, if you ask the vendors, you get into confidential computing. Because effectively, this is a Kubernetes point of view, we are safe with encryption on transport. So this is transport layer security somehow this way, and we are also safe because we can encrypt every disk in the cloud. There are protocols for this. Linux says, "Looks, I have it on my laptop." You need to set up a password, or you have a ceremony in a trusted environment. Then we again fall back to the castle model, and then you have it. What is not guaranteed at the moment is that your memory is encrypted, because memory encryption is hard. You need special CPU technology for this. But the good news is this CPU technology by Intel and AMD will be commodity in the next year. So nearly every CPU will have it. So please use it. The bad news is all the CPUs have inherited some kind of legacy in the microcode, in the firmware. And you have normally, in that case, some uncertainties. And there was some guy from Kiel, Luca Wilke, who made his PhD thesis on that. I've met him virtually several times. And on his site, so the link is on in the presentation, he could take over all known enclave systems by different means. So one thing, the most prominent thing was he changed the DRAM, because RAM is always trusted in a computer. There is no way of identifying RAM and signing RAM DDR4 or DDR5, and therefore everything which says I'm a memory module is trusted. And he used the Raspberry Pi, and it simply said, okay, I'm a 32 gigabyte system. Effectively, have always only been 16 gigabyte, and the encrypted memory was unencrypted into the fake memory. So this worked. And another thing was Intel TDX now spawns a minimal virtual machine, and all the virtual machines had the same hash. So the attestation, which attested effectively the first virtual machine, attested also every other virtual machine. These are bugs, they are fixed, and they are following the standard embargo process. So you get, as a cloud provider or ISP, I don't know who is all involved, get an announcement there will be a CVE, and then the embargo process starts. But implicitly now you are trusting the embargo process. And if the embargo process is as flawed as for SharePoint, then it might be that for 6 months somebody has information about the vulnerability and not you. You have to be aware of this. And then finally you get a firmware fix, and then another 6 months can be that the cloud providers, all the public cloud providers, need to test the firmware in their cloud environment and roll it out. This is another 6 months. So we have months up to a year where the situation is unknown. Period. We simply don't know, and we hope that nothing happens. We have to be aware that this is part of the zero trust, and this is hidden behind the layers of, yes, we don't trust nobody, but we have to trust this embargo process, we have to trust the CPU vendors anyway, and that nobody is abusing these processes behind the scenes. This is not, this cannot be guaranteed in our environment at the moment. Another thing is the attestation. So the attestation checks your firmware and the CPU, and only attests that that everything is valid if you can check it. But the attestation must run on your own hardware. I would never say you should trust attestation in the same cloud as you want to run your payload. This is a problem, that you don't even know where the attestation is. And it makes only sense if your organization is big enough that the people who do the normal system administration are others than the people who do the attestation. If the same guy manages everything and then does the same attestation for the things he had administered, then yeah, you can leave it, simply. And one more thing, Intel attestation is still based on SGX, and SGX is flawed. TDX is set with a virtual machine. So we are not in a stage at the moment where we would say, yeah, we can trust anything here, or everything. So do the separation of admin roles. You need confidential operators. and besides the standard system operators. I already said this, and the entire the entire system has hidden control planes. If you have a Kubernetes cluster, normally you have many control planes. You have the typical Kubernetes control plane, so the API server. But you have a network control plane, normally your software-defined network. You can mix it, then your Kubernetes takes over the control over the network. You have a storage control plane, normally in your NetApp or something else. And you should simply be aware you have more than one control plane. This XKCD says, okay, who is in charge? Effectively, not the president, but the engineer who installed the red button. This means just make it clear who is this guy. And if you don't trust the president, perhaps you can trust the engineer, but you have to check it. Another thing is identity and access management. You also have to trust the identity and access management. Normally this means in our times a kind of key cloak in the system. But if you are in the situation where your cloud provider has outsourced identity and access management to China, you effectively trust China. So this was a 38.3 talk about who is doing the IAM for Microsoft. It's in China. The good news is now the Chinese don't need to hack your cloud because they have the identity. You also have to trust your operations people. This means if you look into it and do this trusted compute boundary business, so the trusted compute base, you have to do this research on every layer, from inside the CPU to the node, to the network storage, infrastructure, and operations. You have to do it everywhere. And then you can try to start up a secure stack, and effectively you start with a trusted boot. Then you have a CPU or GPU enclave. You have an automatic proofed microkernel running a Linux kernel, and this version of Nova is container aware, so it looks into the containers, and then you can start confidential computing virtual machines. And in Kubernetes you always have a lot of complexity, so you have effectively the chance to get a more secure stack. I would not say it's absolutely secure, but you have at least some candidates. And on the other side you get a lot of complexity. And you only can fight complexity with more complexity until it breaks. And you should be aware this is in your Kubernetes cluster. Now you have the complexity of a data center plus a trust center. And this is a lot. So be careful wishing for a Kubernetes cluster. You could get one, and then you are responsible for all of that. Okay. Conclusion. So I'm faster than expected, but we have some time for a discussion. Zero trust is in general good for you, but be prepared to handle the complexity. This morning was a talk about building a public cloud with small ISPs and a standard for a cloud interface. This is a good idea. But effectively, then you are in that same business, and to have, if you have 100 cloud providers, and you spread your payload about every cloud provider, you cannot guarantee that there is not a malicious cloud provider. In Germany, we have at the moment the issue that in some Frankfurt data center, we have Russian, not only intruders. They install the hardware there, and then they are making their ransomware attacks from inside a German data center. So if we would say every ISP can run part of a public cloud, then we multiply this problem. And this means, in that case, we desperately need a working version of confidential computing, or we have to certify a lot of ISP providers. So then everything will be on that level. So please understand it. Analyze your dependencies, not only the explicit one, but also the implicit one. And then, of course, implement it correctly. And if you try to sell it to your customers, please avoid overselling. Confidential computing or Istio solves a lot of issues, but sometimes I have the impression in German health care that they announce that yes, now everything will be secure. So it's a fairy dust spread on a system. And my regular answer normally is, confidential computing will not solve your SQL injection problems or other problems. And try to see it realistic. It is a good idea, but there's still a lot of work to do, mostly for the cloud vendors. And if we would have at least one open source CPU which is fast enough for this, we could look into this CPU and design our systems the right way. But so far we don't have it, and we are heavily relying on Intel and AMD and ARM and Hope and NVIDIA. NVIDIA has the same problem, that they do everything right. NVIDIA is saying to China they don't want to install backdoors, but this means that there already was a request to install a backdoor. So for GPUs, you can also have confidential computing for GPUs, but if there is a backdoor, this exactly does not mean anything to you. Okay, so this is the QR code for the talk, and you can meet me. I'll still be here until I think the bar is closed or something like that. And if you want to contact me, email, Mastodon or LinkedIn, everything is welcome.
Great, thanks to you. We do have quite some time for questions, so please, if there's anything you want to ask, please do.
Yes.
Please limit comments to after discussions so we can have all the questions now.
Yeah.
Yeah, thanks for your great talk. It was amazing to see this. I have a question about this CPU vendor. What's your opinion about the RISC-V architecture? Because that's open source, but how far is it?
It is, if it is fast enough, we should use it. And I've seen the first laptops with RISC-V, but the speed is really limited at the moment. So I want to have it, and then we can use it for this part. And the European Union is doing a lot of work on that, but we should enforce it simply. We should throw as much money on it that it really takes off.
Hi, Thomas. Thank you very much for a great talk. I watched a talk on 33.3 about Virtually Impossible, the Reality of Virtualization Security by Gal Diskin. Highly recommended to watch that. It's about Intel CPU architecture. And you mentioned the RAM is always trusted. It's not authenticated. There's some stuff about processor enhanced graphics, but you can connect anything that's a PCIe device to a CPU, which creates this problem of the trust level within the CPU, and the virtualization only adds insult to injury, and caching doesn't solve anything from a security perspective. So
caching makes it worse, actually.
Caching makes it worse, yes.
Yeah,
you touched upon the ring structure, which is Intel x86, and the legacy problems. What do you foresee for ARM CPUs? You alluded at the end of your talk a little bit to that.
I'm not an expert on CPUs, and especially on ARM. ARM has a similar construct, but I've not look deeper into it, because on the server side, still Intel-like CPUs are dominating. Definitely, this would be worth a talk of its own, but I've not done it. And same with RISC-V, because by the license you can mix ARM and RISC-V on the same chip, and then you get a very interesting CPU, but I don't know how to judge the risk. And I don't know even somebody who is able to say something about the risk. Unfortunately.
But isn't this kind of even more problematic and pointless to do confidential computing than you mentioned about the firmware lag? Because, for example, there's Rowhammer, and there were different variants of Rowhammer, one after another. Every half year there's another one. There's Spectre and Meltdown stuff, and every half year there's another variant for the next CPU generation. None of those could be fixed in firmware, really. Some could be mitigated slightly in maybe software sometimes. This means that you have to throw away your whole computer every half year, effectively, which will never happen. So why do I bother?
Effectively, what you need to do is you need to look into the software you run. So this means effectively you only can trust open source software on your hardware, because at least you can inspect it. And the cloud model will not go away, because the big machines now have 4 and more terabyte of RAM, and there are effectively no single workloads who can use this thing except SAP HANA, and this means you have to coexist with other people on the same hardware, and the only vision I see is only run validated, scanned open source software on that. But this does not solve any. This mitigates the problem. It's not solving it.
So it exactly doesn't mitigate your problem, because the problem is the other people not running the certified, tested, good open source software. It's everybody else doing the Rowhammer and other stuff.
Then just allow only signed containers or signed virtual machines which have been inspected before the signing process. This is then you have to trust the signing process. Another one bites the dust. This is the problem is not solvable at the moment. Unfortunately. I'm with you. I feel the pain.
You mentioned that trust and zero trust. Actually, I think there's maybe 3 scales. There is trust, which is 1. Zero trust is neutral, and distrust is -1. So you could score and you could attest certain containers that have that level of validation, as you rightly pointed out with the attestation. What's your view on that?
Yeah, effectively, explicit mistrust means don't run this somewhere. If you mistrust something, what I've learned on this conference, so this conference was actually great, even talk to people, there are some companies which forbid to analyze the risk of running Microsoft 365 or Azure, because they know the answer. So this is on an Orwellian level, this is another level. So if you are not allowed to analyze the risk, then you are done. This is a corporate equivalent of don't look up. So and I posted it on Mastodon. Don't look up is a corporate order now, and I don't know what. I cannot handle this effectively. So run your own stuff as much as possible, but you are limited. You cannot run everything on your own hardware.
Yeah, you said about the huge machines with terabytes of RAM, but if you're, for instance, in a government, you don't have to buy these huge machines. You can just separate, go back to hardware separation.
You can, yes. Effectively, the government data centers are pretty small, in the range of 20 megawatt. 20 megawatt is nothing compared to the gigawatt data centers which are built now. So effectively, a government does not have so much need for memory, except if you do something with maps or with, but then most of it is public. And the government should really analyze it, what it really needs. So I guess for the standard thing, if you say everybody in the Netherlands or in Germany has one government contact a day, it's not really much compared to watching a video or something like that.
But then that's also the solution to your problem. Just buy smaller machines that you don't share. And another remark, I liked the nuclear... can you show the slide again? Can you show the slide with the nuclear thingy?
The nuclear button, yes.
Yeah, that one. That's a perfect example of zero trust, because when they installed the security codes with 8 digits, you can guess all the 8 digits. They were, for the first 20 year, they were all 0.
Yeah. Yeah. That's what Clinton was. And now it's 1, 2, 3, 4, 5, 6, 7, 8, probably. Or this is you cannot solve the problem. You have to. You have to trust. To build trust on every layer, and the government. If normally humans are on layer 7 or 8, and then the government is on layer 14 or something like this, and if you cannot trust layer 14, it doesn't matter what happens on layer 1. It really doesn't matter. If the entire US government is open to every hacker in the world, and it looks like now, then you don't need it. They lost the they lost the blueprints for their nuclear weapons, so what else can be stolen? So we can stop now. So we are in a happy post security age, and now we have to protect the things we can protect. So critical infrastructure, electricity, water, transport, and that.
Okay, so resilience instead of security.
Yeah, of course we have to change our model to resilience. So stay stable.